Group B, and this is our challenge 6. Okay. Let me check. Okay, everything's okay. And we use antique dataset provided by CIRR UMass. The raw inputs come from multiple official files, the document collection, training, and test queries, and query for relevance labels. There is also an optional blacklist for or filtering some test queries. Because these sources are separate, the first thing we do is to standardize everything into one unified table that all models can reuse. And this slide shows the key deliverable, a tidy data frame that merges all sources into one consistent schema. Each row represents a query, document pair with the query text, the candidate answer text, and a relevance label from 1 to 4. We also attach a split tag, train, valid, or test, so every teammate can train and evaluate using the exact same data definition. This is crucial because it removes ambiguity and prevents each model from using slightly different preprocessing. And our basic state, here are the basic states after building the tidy data frame. In total, we have 33,174 query document pairs. We create 3 splits, 21,613 for training, 5,809 for validation, and 5,752 for test. These numbers are exported to our basic states CSV data, so the whole team can reference the same data set size and the level distribution when reporting results. And this is our candidate per query. We look at how many judged candidate answers each query contains based on the training files. The histogram shows that most queries only have a small number of judged documents. However, there is a clear long tail. A small portion of queries have many more judged candidates. This matters for ranking because query difficulty and evaluation stability can vary depending on candidate size.
Very good.
Okay, and the relevance level distribution. We summarize the distribution of relevance levels from 1 to 4. This is not just descriptive. It's used to define our evaluation rules for binary metric like MRR, MAP. We need a threshold to decide what counts as relevant. Yes, and like NDCG, we need a gap mapping so that higher relevance levels contribute more to the score. Both the table and the plot are saved as shared artifacts so that the entire team use identical definition. And this is one of the most important design choice. We slipped by query ID, not by individual rows. That means all documents associated with same query must stay in exactly one split, train, valid, and test, or test. The reason is to prevent query leakage. If the same query appears in both train and validation, models can implicitly memorize query patterns and overestimate. Yeah. And this is our flow.
Yeah, let me explain the flow to me a second. Yeah, raw data, query, collection and queries. Group by query ID. Each query ID has multiple docs. Split query ID, train, test, validation. Train all docs under the query ID. Okay, good, understood. Yeah, very good, very good.
Yes. And our matrix skeleton. To ensure consistency across the team, we implemented a shared matrix model. MRR emphasizes how quickly a system returns the first relevant document, and the MAP measures ranking quality across all relevant documents by averaging precision and relevant position, and the NDCG at 10 focused on the top of the rank list. Yeah. And for finally, we define the relevance mapping rules used by our metric for binary relevance metric like MRR, MAP. We treat labels 3 and 4 as relevant and labels 1 and 2 as non-relevant. For graded relevance in NDCG, we map labels 1 to 4 into gains 0 to 3, for example, using gain equals labels -1. Yeah. And that's all for my part. And let's move to the other.
Can you give me a
member.
second? Can you give me a second? I have to take care of the baby a second. I'll just bring her down and I'm gonna be right back. Give me a second.
Okay.
And you're back. Go ahead, please. So Martin, so you binarize the label. Go ahead. Task 2.
Okay.
Hello.
So I'll be covering the task 2 part. Okay, in task 2, our goal is to transform question answer text pairs into numerical features that can be used by tree-based learning to rank models. And instead of directly feeding raw text or embeddings into the model, we design explicit pair-level features that capture both semantic relevance and lexical matching signals. And these features are later used by the ranking models in task 3. Okay, next page. And we use a pre-trained BERT model, BERT based on case, to encode questions and answers separately. For each text, we take the CLS token embedding as a 768 dimensional sentence representation. At the pair level, we compute multiple semantic features, including cosine similarity, element-wise product, and an absolute difference between the questions and the answer embeddings. And this allows the tree model to learn nonlinear interactions beyond a single similarity score. Okay, next page. In addition to semantic features, we also include several lexical and metadata features. These include questions and answers lengths, token overlap count, J-curve similarity, and TF-IDF overlap between the question and the answer. These feature exact word matching signals, which are often important in information retrieval and complement BERT semantic representations.
So this TF-IDF, what is it? What is the TF-IDF metric? TF-IDF, what does it stand for? Term frequency inverse document frequencies. Yeah, calculates the word importance in a document relative to a collection by multiplying the term frequency TF by the inverse document frequencies. Got it.
Okay.
Yeah, nice. Okay, good. Go ahead.
Okay, next page. And to verify our features, we visualize the cosine similarity distribution and inspect several queries manually. And we observe that more relevant answers tend to have higher cosine similarity, but highly relevant answers do not always receive the highest scores. This confirms that cosine similarity alone is insufficient and motivates the use of learning to rank models to combine multiple features.
Excellent.
And next page. And this page is the visualization, shows the analysis of the BERT cosine similarity features. And on the left, we display several examples queries where candidate answers are ranked by cosine similarity between questions and answer embeddings. We can see that more relevant answers generally have higher cosine similarity, but the highest relevance answer is not always ranked first. And on the right, the histogram shows the cosine similarity distribution overall question answer pairs in the dataset. Most pairs have relatively high cosine similarity, and the score ranges of different relevance levels overlap significantly. Okay. So this is the end of my part.
Okay, so the next is my part. My part is to present the baseline random forest model. So for this, okay, so for this experiment, we utilize a random forest classifier. Our feature engineering focus on two fundamental lexical metrics, cosine similarity and Jacob similarity, which measures the textual overlap between the query and the answer. We binarize the relevance scores, treating anything rated 3 or above as relevant, as the slide shows. Yeah. Okay, next page. Okay, so let's look at the performance. Our baseline MRR is 0.6254, but notice that the metrics on the left, our recall is strong at 0.73, meaning we are finding most of the relevant content. However, our precision is low at 0.39. If you look at the confusion matrix on the left, the top right number is alarming, which the number is 2,532 false positives. This indicates that our model is aggressive. It classifies many irrelevant answers as relevant, introducing a significant amount of noise.
Excellent.
In this page. Okay. To understand why we have so many false positives, we analyze the prediction score distribution. Ideally, the blue curve, which indicates the irrelevance and labeled by 0, should be on the left, and the red curve, which indicates the relevant parts, should be on the right. Instead, as you can see, they are almost stacked on the top of each other, peaking around 0.6 to 0.7. This explains the low precision to the model. The relevant and irrelevant data points look nearly identical. Next page.
Excellent. Yeah, very good.
Okay. So here comes the question: why can the model separate the relevant and irrelevant parts? Looking at the feature importance, cosine similarity dominates the decision making. The model relies entirely on keyword overlap. Take this case study. The user asks for the definition of weed. The top 3 recommended answers have scores over 0.9, but they are all wrong. They discuss movies or personal stories, imply simply because they contain the word weed multiple times. The model sees the keyword match but fails to understand the actual semantic intent. Next page.
Just a second. So the movie, just go back one slide. So the movie that they refer to is actually it's a propaganda movie. Let me send it to you now. Referee Madness. It's a movie from the 1930s, right? Because I mean, we're always talking about movies in class, right? So we should talk about movies today as well. So this was a propaganda movie that was made in the 1930s, where there was somebody that they smoke marijuana and they ended up committing a murder, right? So the movie is relevant because it created a lot of stereotype about smoking weed. So the relevant, just not the answer.
Yeah,
Exactly. Go ahead.
yeah.
I just wanted to mention the movie. We're always talking about movies. Go ahead.
Totally get you. And okay, so next page, please. Okay, so we are going to the conclusion of my part. So first, our baseline demonstrates the limitation of lexical matching. It creates high recall but low precision. Our immediate next step is to introduce semantic embeddings, such as BRT. This will allow the model to judge relevance based on meaning rather than just appearance. Okay, and we expect this to significantly reduce the false positives seen in the case study and improve our precision. So I'm moving the presentation to the next speaker.
Hello.
Hello,
Okay, so
hello.
in this section, I will present our learning to learn approach using LambdaMART along with an exploratory study on synthetic personalization. And the focus is not only performance, but also ranking behavior and interpretability. And next slide, please. So point-wise models treat each question and answer pair independently. However, ranking metrics depend on the relative order of answers within the same query, which motivates learning to rank. Next slide, please. LambdaMART is a list-wise ranking model based on gradient boosted trees. It uses lambda-based gradients to directly optimize ranking metrics such as NDCG, making query group essential. Next slide, please. So we perform a query-based training validation script to avoid leakage. Features include TF and IDF cosine similarity, length features, and lexical overlap measures. The label distribution is highly imbalanced, which is common in ranking tests. Next slide, please. So this table compares ranking performance between the base and personalized LambdaMART model using MRR, MAP, and NDCG 10. Personalization shows slight improvements on some test metrics, but not consistently across all measures. Okay, next slide, please. So feature importance analysis shows that semantic similarity dominates ranking decisions, while lexical features still contribute meaningfully. Next slide, please.
Wow.
Okay, so we next introduce synthetic personalization or SPICE. Since NDQ lacks real user data, this experiment is exploratory and qualitative in nature. And next slide, please. So we construct a user profile by averaging TF and IDF vectors from 5 historical answers. Cosine similarity to this profile is then used as a personalization feature. And next slide, please. So this slide shows a top 5 ranking comparison for the same query on the base and personalized models, while the ordering remains identical. Personalization weighs the confidence scores. And next slide, please. So overall, personalization acts as a soft bias. It does not override global relevance, but integrates in an interpretable and controlled manner. And
Yes.
next slide, please. In conclusion, LambdaMART outperforms point-wise models by aligning better with ranking objectives. Synthetic personalization provides an interpretable and controlled way to incorporate user-level signals. Next slide, please. And this is our performance.
Very good. Let me just take a couple of notes on my page deck. So you guys said that over retrieval. It's very good, very good, very good. So you said over retrieval, right? Over retrieval, lots of false positive. Very good, very good. Very nice. So you couldn't really get the BERT embedding to work then, right? That's a final message, right? Even if you use the BERT embedding, then this the inverse frequency is still the most relevant feature, correct? In the decision making. Interesting. Yeah. Okay, very good. Yeah, and of course the final exercise with the history of the question was just something that I was trying to imagine, right? So of course, as I said, it just works as a soft bias. Okay, yeah, very nice. Then you also had the distribution of the correct, relevant and irrelevant answer. There was also a good figure, right? That you showed that the difference in the two distribution is very small, right? So basically, it means that if you have multiple question and answer, you can look at the distribution and try to decide. You can distinguish the two distribution, the correct and incorrect, but on the single sample, then it becomes too difficult to distinguish them. Okay, very good, very good. Yeah, very good. Any questions? I mean, any other comments, guys? Anything that you want to ask me? Anything that you want to add to the presentation?
So the final presentation is on January 14th.
Yeah, let me just double check because I'm very terrible with dates, right? So let me just check that the 14 is, yeah, in 2 weeks, correct? So the 7th is going to be the next one, and then we have the 14th, correct? Yeah. Okay. Did you guys started looking at the final presentation? Do you guys, I mean, yeah, you start working on it or not yet?
Not yet, because we were working on optional challenge.
Yeah. So you like to work together so much, right, that you decided to spend all your time working together on both challenge 6 and the final presentation. Very good. Very good. Group B for the win. Very good. Very good.
Thank you.
Okay.
Okay.
Thank you so much, guys. Okay, very good. Then I'll stop the recording. Yeah. If you have any other questions, you let me know. Otherwise.